Morning, everyone. This is going to be a short video on approximating double integrals, and I wanted to save this. This is a concept from earlier in the chapter, but I wanted to save it until we had a better idea of what regions were and sort of what this double integral represented. So just as a reminder, I wanted to start off by looking at this double integral. So the basic parts of this are these numbers here represent the region that our double integral is over. So it looks like x in this case is between 0 and 3. So I'm just going to draw that region, right, 0 and 3 down here. And then our y value is going to be in between -2 and 2. So that's 3, and then y is going to be in between -2 out here and 2. So our region that we're going to be integrating over looks something like this. All right, so that's what's on the floor. That's our projection of our solid. This f of x and y piece here, right, so I'll kind of fill in that region. This f of x and y piece here, this is our surface, right? So this double integral, once we solve it, this whole thing represents the volume under the surface over this region. So I'll go ahead and just draw some generic surface. I didn't tell you what this is. Maybe it's something like x squared times y squared, or sine of x times sine of y. But I'm just going to draw some kind of generic function for now. Right, something that looks like that. So our double integral is going to be this volume underneath the surface. Right, this is what we say, z equals f of x and y. So volume underneath the surface over the region. Y is between -2 and 2, x is in between 0 and 3. If we had a function for f of x and y, then we could just solve this double integral, maybe use Fubini's theorem to solve that. But this topic is about approximating double integrals. And so what we can do if we want to approximate this volume here is we can break this up into little rectangular prisms. Right, that might look something like this. So I'll go ahead and draw a more isolated, zoomed out version of this over here. I'm going to try my best to keep the color scheme for this consistent throughout this whole lecture so that you can kind of see what's the same. But yeah, it's just a rectangular prism kind of hanging out there. And the idea is if we add up all of these rectangular prisms, and if we add up enough of them, then that's going to approximate this volume. So just talking about the dimensions of this, we're going to label them generically for now. This is going to be delta y across this side. This measurement here is going to be delta x from here to here. Actually, I'm going to move that over. I started off saying this was a short video, but I'm sure you'll see on YouTube how long it actually is. There's kind of a lot to say about this, but anyway, delta x and delta y. And then this height here, if you want to think about how tall this rectangular prism is, then we should be looking at sort of this here. Let's say maybe this is the point 1, 1, and then on the floor, so 0 for our z. We want to think about how tall this rectangular prism is, and the idea is that we stop right here where it hits the surface. So this rectangular prism might be poking out from the top or be underneath the surface in certain spots, but right at this point that we're talking about, it hits the surface exactly. So the height of this particular rectangular prism is going to be f of 1, 1, right? The z value when we plug in 1 and 1 into this equation. So that's what that looks like. More generally, we kind of call this, since we're going to be making a whole bunch of rectangular prisms here, this is going to be f of xi and y of little j. So I'll talk about what these I and j mean in just a second, but you may recognize this from Calculus 2 when you approximated the area under the curve. We had these kind of star values, and in summary, what these asterisks mean is that you can either take the left-hand rule, the right-hand rule, or the midpoint rule, but just whatever value you end up using to kind of define this little point here and this little point here, that's going to be your x star and your y star. So yeah, height of this thing is going to be the function evaluated at this point. So what we can say is if we want to approximate this volume underneath the surface over this region, let's see, so dx, dy, that this is approximately equal to the volume of these little pieces, so leave some room here. It's approximately equal to the volume of each of these, so I'm going to call this f of xi star yj star. Delta x times delta y, we can simplify that to be not dA, delta A, right? Delta x times delta y. And then instead of integrating across these with infinitely thin rectangular prisms, what we're doing is we're just going to be adding up. Maybe we have 13 or 12 of these rectangular prisms to add up. So we use a double sigma here. The way that we work with this is we say that we'll start off by saying I is indexed from 1 to m, and j is going to be indexed from 1 to n. So if you've ever taken a programming class and you had to do a for loop, this is sort of like the for loop. I is from 1 to m, and then you're nesting that, or you're putting that for loop inside of another for loop for j from 1 to n. Add this up. All right, so you're kind of adding up across the row, and then you're adding up that row across all the columns. I'll just write a quick note here. It says, just remember that delta A is equal to delta X times delta Y. Okay, so this is us approximating the volume set up by this double integral here. I don't think it's going to do you a lot of good to just simply memorize this formula. You really need to be able to do this in the context of a problem. And the way that you can do that is to just be able to think about what each of these pieces represent. So I'll give an explanation of that now. So let's say that you're given this. Let's talk about that same region. So that region was in blue there. So again, this is 3, this is -2 to 2. And this is our region in the middle here. Suppose that I gave you the task of approximating, so we can approximate volume under the surface using, let's say, m is equal to 3 and n is equal to 8. These m and n are coming from this piece here in the summations. So I'll just state it this way, that m relates to delta x and n relates to delta y. And I think it's better to show you what I mean than to try to explain it too much, but m is the number of separations that we make, or the number of little compartments that we're going to make in the x direction, and n represents the number of separations we're going to make in the y direction. So when we approximate Vm is going to be equal to 3. That means that we want 3 sections in here. So that one's going to be fairly easy to figure out. If we separate this in 3 compartments, we get 1 and 2 for each of those. So we can say here that delta x is equal to 1. For n, you might just be able to kind of guess your way into figuring this out, but the consistent way to figure this out is to kind of take the entire length of this y direction here, which, being super technical about it, this is going to be 4, right? The distance from here to here. So we have a distance of 4, and then delta y is going to be equal to 4 divided by this number of partitions, n. So that's 4/8, which is just equal to 1/2. And if we set our delta y's to 1/2, so I'm going to sort of take care of this methodically by splitting it in half, splitting it in half again, and then splitting each of those parts into half. So now I can see that I have, this would be 2, 1, 0, -1, and then this will be 1, 2 for those pieces there. So I have delta x, that's 1. I have delta y, that's 1/2. And I, of course, can say that my delta A is equal to 1 times 1/2, which is just 1/2. So that'll be my delta A in my equation. We're given m and n. And then if you're given a function, you can figure that out as well. One thing that I want to mention while I have this drawing up is that if we think about the analogy to what we do in Calculus 2, when we're trying to approximate this area, so this would be y and x, if we're trying to approximate the area under the curve, let's say we're going from, I don't know, 0 to 4, and our delta x is equal to 4. What we'll do is break this up into 1, 2, 3, 4 components. And then the choice that you have is you can use the left-hand rule. You can use the right-hand rule, or you could use the midpoint rule. So what that means is you can think about how many of these rectangles you want to make to approximate this area underneath the curve. If you use the left-hand rule, you're always going to be using that left-hand piece to define what the height of this is, right? So this is sort of like your f of x star component. And then we stop there. So here it's pretty easy to see that you need 1, 2, 3, 4 rectangles, and that you evaluate them at 0, 1, 2, and 3, and then 4 doesn't get its own rectangle. For the right-hand rule, all right, you kind of start with this right-hand rectangle, right-hand, right-hand. So now we're evaluating them at 1, 2, 3, and 4. Those are our points that we plug into the curve to see where we evaluate it. And then the midpoint rule is in the middle there. What I want you to notice about this is that each time we're only making 4 rectangles here, right? So the analogy here is that when we have m is equal to 3 and n is equal to 8, we're only going to be using 24, or m times n, of these rectangular prisms to define this. The reason I mention that is because it's really tempting. Let's say I told you to use to approximate this volume, and it's really tempting to go through and look at every single one of these intersections, right? Because we have all these nice integer values, or maybe the 1/2 values. It's going to be really tempting, so on and so forth, to go through and collect every single one of these values that we can. The problem with that is we have 1, 2, 3, 4 times 1, 2, 3, 4, 5, 6, 7, 8, 9. So 4 times 9 is, 36. So we only want to create 24 of these rectangular prisms, or we only want to choose 24 points to actually use to approximate that volume. So if you choose the midpoints, right, it might look something like this. Well, I'm gonna make a couple copies. I can show you what these look like. So for this one, we have more than just the left-hand rule, the right-hand rule, and the midpoint rule to choose from. We've got basically the middle. Well, we've got a lot of options, I guess, is what I'll say about that. So we could be choosing these 24 in the middle here. So if you think about that f of xi star yj star, the values that you're going to be plugging in here, for example, this one here is going to be 1.5 and 1.5 for x, and then 3/4 for y. So you'll have a bunch of fractional values in here. Another option would be to say, maybe I'll talk about the lower right corner. So in that case, you'd always use the lower right. And if you do that, note here that you're missing out on a whole row and column of potential values that you could be using. But if we want to approximate that volume under the curve, this is always going to be an overestimate, a really big overestimate. That would be like, having 5 rectangles here. So we only want to have 24 rectangles, rectangular prisms in this one. And I think you get the idea, but right, the top left corner would be something like that, so we can use all this stuff here. Either way, we'll say in all cases, make sure the number of points or we'll call them terms, since we're going to be adding them all up. In case, make sure the number of terms is equal to m times n, and that is 24 in our case. Okay, I'm going to run through an example. So I would like you to approximate the following. And I'm going to define the region in that way that we saw at the very beginning of this chapter, where I make it the cross product of 2 intervals. So I'll give us some nice short numbers for this. Here our f of x and y is just going to be x times y, and our x is in between 0 and 6, and this is in between 0 and 4. So the actual double integral here is xy dx dy. Just to point out, let's see, x is in between 0 and 6, y is in between 0 and 4. We could absolutely figure out what the exact volume of this is. This is not a difficult double integral to do by any means, but I just figured I would choose something nice and easy for our first description here. So we're going to use m equals 3 and n equals 2. So this is approximately equal to this. So I is going to be from 1 to 3, and j is going to be from 1 to 2. We have our function here, so this is x I star times yj star. I would probably write, personally, I would just write x times y here, but technically this is what you should be doing. I certainly won't mark you off if you just write x times y. That's what you're going to be doing. And then times delta A. So I would suggest drawing a sketch of what's going on here. So here's x, here's y. So y is going to be between 0 and 4, x is going to be between 0 and 6. And m is equal to 3. So I can either use that formula that I mentioned earlier, which is just this length, 6 minus 0 divided by 3, but I think this one's pretty easy to see that it's just going to be 2 for my delta x. And then my delta y is also going to be 2. I didn't specify which I wanted you to use, whether I want you to use the midpoint or the top left corner or the top right corner, but I think in this case the midpoint is nice, especially now when we can use whole integer values. Right? So this is going to look like this one, for example, is going to be the point 1, 3, and that'll be nice. Working with those with our integer values. Okay, so I suppose I could write out what my delta A is equal to. So delta x, right, and delta y. Delta x is equal to 2, delta y is also equal to 2. So that means that delta A is going to be equal to 2 times 2, or 4. So from above here, this double summation is going to be equal to 4, that's my delta A, times every single one of these function values evaluated at each of these points. So I'll start at the bottom left corner there. This is f of 1, 1. Summation means plus, so we're adding all these up. f1, 1, f3, 1, f1, 3. Three, 3, f, let's see, 5, 1 plus f, 5, 3. Just notice that we've got 1, 2, 3, 4, 5, 6 terms, which is m times n, so that's good. Just a nice double check to have. Again, it's tempting to get every single one of these intersections, but we just want the 6 points there. So these 6 midpoints will do it. This is going to be 4 times, so f of 1 and 1. Remember, our function here is just going to be x times y. So 1 times 1 is 1. So on and so forth. So this is equal to 4 times 36 and that is equal to 144. If you think about the actual value of this, I might ask you to say how good of an approximation is this. So just keep in mind that this double integral that I wrote up top there is something that you could solve, and then you can compare that value to the approximation that we have here. But that's all I wanted to say about this. There is a problem that is on WebAssign where you're trying to approximate the volume of a pool, and so you're given a table of depths. That has some values at 1, 2, 3, 0, 1. Maybe it looks like this. 0, 1, 2, 3, 0, 1, 2. So the idea is you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points in this example. But you really want to draw out what your region looks like and divide it up in terms of the m and n that you're given. Because when you go, excuse me, to make that double summation, you're not going to want to use all 12 of these points, right? That would be equivalent to kind of taking all of these points here, but that's going to give you an overestimate. So good luck with that problem. And in the next video, I got a couple emails of people asking questions about some of the homework problems on WebAssign. So I'm going to go over solutions for that.